So in this example here, we have one transformation that goes from this picture to this picture that's actually made up of two simple linear transformations. Our first linear transformation is a 50% compression along the y-axis, and then our second transformation is rotating this picture 90 degrees. So with a linear transformation, all we need is a matrix to describe what happened. So we're going to find that matrix in two different ways. The first way is we're going to track vector E1 and vector E2 through the two steps and then use the structure theorem to get a matrix. The second way, we're going to find the matrices of each of the transformations separately, and then we're going to put them together to get a final matrix for the transformation. So let's start with the first way, which is tracking our E1 and E2 vectors. So a way that I often like to solve transformations is I write out my original vectors, and then I write out what they are transformed for the first transformation, so it's 50% compression. And then my last transformation, which is 90-degree rotation. So let's start with E1, which is equal to 1, 0. So we want to draw our E1 on this diagram here. There's our E1. So our E1 is going to be 1, 0. And our E2 goes along the y-axis, and that's 0, 1. Now what happens to our E1 vector? So let's see. So we take this step here, it actually stays the same because we're just compressing along the y-axis. Nothing is happening along the x-axis. So that stays the same. Now what happens to our E2 vector? Well, we're compressing 50% along the y-axis, so that means our y value is going to get squished by a half. So 1 turns into a half. Now for our 90-degree rotation, our 1, 0, which started out here, is going to go up that way. So what we end up with is 0 on the x and 1 on the y. So let's just trace those. So E1 goes there, then it gets rotated up that way. And you can see here it stays the same length. Now for our E2, it's been squished there, and now it gets rotated over there. So now we have negative a half for our x value, and we have nothing, 0 for our y value. Now to put these together into our transformation matrix, we can use the structure theorem. So we have our transformation matrix A is equal to our transformed E1 vector and our transformed E2 vector. So our E1 vector is over here, our transformed E1 vector, sorry, so we sub that in. And here's our transformed E2 vector. And there, this is our matrix describing the transformation. So now let's try it in the other way. So in this way, we want to find a matrix for this transformation and then a matrix for this transformation separately. So let's just fold this over. So let's take the same sort of steps that we did with the other question. So we have our original, and then we go to our compressed. So our E1 again is 1, 0. It's our E1. Our E2 is equal to 0, 1. And now to go to the compressed, we end up with 1, 0 still for our E1 vector, and 0 and a half. So the matrix for this one transformation using the structure theorem is this. So we have our transformed E1 vector and our transformed E2 vector. Now let's just forget about this for a second and pretend this is our original picture. So let's just call that original 2. So now just look at this picture instead of this picture as our starting point. So we have our E1 vector is actually the same in this case. And our E2 vector is actually going to go up to here, because our E2 vector is equal to 0, 1. And now when we rotate, our E1 vector goes up to there. So we have 0, 1. And our E2 vector goes out to here. So we have negative 1, 0. Now let's make a matrix for this transformation. So here's our transformed E1 and our transformed E2. So now to put these two matrices together to find out what any transformed vector would look like, we're going to take our first transformation and apply that first to our vector, and then we apply our second transformation. So what that looks like is we have our last step. That matrix actually goes first in this line. Then we have our first step, and that actually goes last in the line of matrices. But if you look at it, how we solve for vector u, we actually hit our vector u by this matrix first, and then that gets hit by this. So the order that we calculate it follows this order, but the order that we write it is sort of backwards. So this is our last step matrix, and this is our first step matrix. So let's just calculate that matrix multiplication. So this is just like finding dot products. So we have 1 times 0 plus 0 times negative 1. Then we do the same thing with the next row. So 1 times 1 plus 0 times 0. Then we take the second column and hit it by the first row. Then we take the second column and hit it by the second row. So now we have our matrix for the whole transformation is equal to this, which if we look back to the other way that we solved our problem, it's the same matrix. So what this tells us is that the matrix of the composition of two transformations is the product of the two matrices for each of those transformations. So here is our final transformation matrix, and that is a multiplication of our first transformation matrix and the second transformation matrix.